Welcome everyone. My name is Nicolas Araque, and alongside my fellow researchers Mario Catapano and Massimo De Gennaro from the Universidad Metropolitana de Caracas, we are going to present our work titled Study, Attend, and Predict Academic Performance Prediction Using Transformers. I want to thank LatinX for their work organizing this workshop and all of you for your attendance and attention. Starting with our presentation, we are going to talk about the motivation of our research. Education is established to be a key factor in the social and economic development of Latin America, and the machine learning and artificial intelligence community can help to improve this development, creating tools that empowers students to improve their performance. Going deeper into this statement, we found that many universities offer flexibility for course enrollment when cursing a major. This enables students to personalize their schedule, choosing how many and which courses they want to enroll in the next term with certain restrictions as course prolongations. On the other hand, this flexibility can be harmful. Students with no information can make bad decisions, resulting in low GPA, extended career times, and even student dropout. For example, we can see Carlos on the slide. We need to decide what courses to enroll in the next term from these 7 possibilities. He can select from 3 to 5 courses, but the only information about these courses is the online program and the people he knows that have already passed the courses. He can also think empirically about the relations between past courses, the grade that he obtained, and how this could influence his performance, but nothing is sure. If Carlos enrolls in too many courses, or a lot of difficult ones, he can fail several courses and obtain an overall low GPA. But if he enrolls in few courses and discovers that they are easy ones, he has lost an opportunity to advance quickly in his major. From a machine learning perspective, we can help Carlos with this problem using his past grade or academic performance as a sequence, where each term is a time step. Then, we can create a model that predicts his performance on the next term. If he uses the model with several possible course combinations, he can identify in which he has better possibilities of obtaining a passing grade. This is not a novel approach, and educational data mining has been around this for a while. Nevertheless, we want to differentiate this approach from a predicting student dropout, which has been extensively applied in university settings. Predicting dropout students enables a university to identify students at risk, and with this identification, they can take corrective measures like counseling. The dropout prediction approach tries to help all students, focusing only on high probability dropout students. Our research aims to use the detailed academic performance history database from the university to train a model using the transformer architecture to predict the probability of obtaining a passing grade on every course on the next term to be enrolled. The model needs to take into account not only the specific courses to be enrolled, but the number of courses and their combination. Following Carlos' example, we want to condition the probability of success in every course with the grades from past terms and also the desired course to be enrolled. This is going to allow Carlos to decide if he is planning to enroll in too many courses or a combination of 2 difficult ones.
We collected a dataset containing 822 different students over a 7-year period from 2011 to 2017 from the System Engineering major of the Universidad Metropolitana, containing the courses and grades obtained by these students in each term, with a total of 23,719 courses and 6,053 different terms. There are 67 different courses, with grades ranging from 0 to 20 and 10 as the minimum passing grade. In the dataset, there is an imbalance because the majority, 69.21%, of courses were passed. The train test split was carried out with 739 students for the train set and 83 students for the test set, and no overlapping. We use the encoder structure from the transformers architecture, but discarding positional encoding, where one vector has all numeric representations of each course, and every 7 positions is a term. If a student has less than 7 courses in a term, the rest of the positions are filled with zeros. Then it is included the courses to predict previously embedded and concatenated with another vector with the grades for each course, where each course is in the same position as the corresponding grade in the first vector. In summary, for each student, we created 2 vectors of 161 positions, 23 terms multiplied by 7 courses, and these vectors are used as input for the model. One vector has all the courses, and the other one has all the grades in the previous terms. We have not been able to develop a pertaining embedding of the course information, so we instead use a random embedding that is trained with the model parameters. The output is a vector with 7 positions, where each space represents the probability of passing each course selected within that combination of courses. The model was trained for 10 epochs using the Adam optimizer and binary loss function.
With our model, we were able to achieve an accuracy of 73.6% and an F1 score of 81.26%. You can see in the results shown in the confusion matrix the consequence of the imbalance of classes previously mentioned, where the number of true positive is far greater than the number of true negative. We show the UMAP2D representation of the resulting embedding of courses, and you can see that the model learned that some similarities exist between courses of related academic areas, such as math courses and physics courses. For future works, we plan to make a model using positional encoding, retrain the courses embedding, and decide what models we can take as reference to compare results. As it is a work in progress, the results are not definite, but the following conclusions were reached. It can be observed in the results that it is possible to use academic records as input for attention models. In turn, it can be observed that the transformers architecture can make use of these mechanisms to effectively fulfill the task of predicting academic performance. And it is possible to train a randomly initialized embedding of courses. And with that, we have reached the end of our presentation. Thank you all for your attention, and thanks to the organizers of this workshop for making this possible.